Regression Analysis 2, Holding All Else Equal. So what we're going to talk about here is how regression allows you to hold all else equal, how that works. And what we're doing now is multivariate regression. So rather than just have one x and one y, you can have multiple x's. So where we saw the regression of y equals mx plus b, let's rewrite that so the intercept comes first, because that's a common way to write a regression equation. So y is equal to b plus mx. And the multivariate form is y equals, these are betas, beta 0, that's the intercept, plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. The betas are the slopes for each x variable. We use betas a lot in economics in regression, and so I'm just using them here because it's standard. Okay, so I think I already said that. No, here's another thing I want to say about this. The beta 0 is the intercept. Those other betas are the slopes, but what do I mean by that? They're the partial derivatives, the effect of each x on y holding all the other x's equal. So remember, that was what a partial derivative did. It kept the other x's or the other arguments in the formula constant and just told me what's the effect of the change in 1x. Okay, so this should look familiar from the first part of the class. This is a linear function, and it asks what's the effect of a 1 unit increase in income. So income typically, as you know, is given as a y variable. And so holding all else equal, a 1 unit increase in income leads to a 5 unit increase in quantity demanded. That's the partial derivative. And that's exactly what a regression model is. It's a linear formulation where you're holding other things constant, and you're going to find the effect of each variable on the y variable. So the coefficient, that's the beta, for each x variable tells you how that variable affects y, controlling for all the other x's. I just wanted to put that in as a definition. That's how we talk about it, that we're controlling for the other x's. And it's very, very powerful, because what it means is that you can disentangle different explanations from each other. You can see the independent effect of x1 and the independent effect of x2, and how they both affect the y. So for example, you can use a regression to estimate how education affects children's health independent from income. Two scatter plots can show you that both income and education are positively associated with children's health. But it could be that income alone matters, and that education is just standing in for income, since the two are also positively correlated. So how do you know which one contributes? Do they both? Is just one? How does that work? So here's a picture that demonstrates this. So figure 1 is infant mortality and income in 2010. And I have infant deaths per 1,000 live births on this axis. And then I have a bunch of scatter plots going along the GDP per capita. And what's this figure? So you can see anyway that the more income, the lower the infant deaths, the lower the infant mortality. Same relationship appears to hold for infant mortality and college enrollment. So in countries where you have lots of people, this is the percent of college-age population, lots of people enrolled, infant mortality is pretty low. In places where there's not a lot of education, infant mortality is pretty high. It's a negative relationship. Okay, so I went ahead and had Excel draw the regression line, and here it's written out. Y is equal to, here's the beta, here's the coefficient on x, and then here's the intercept, and the same thing here. And then I've written it out here as well. So the line that's estimated is that infant mortality is equal to, here's the intercept, 36. So if you have no college education at all, that's what I'm going to guess your infant mortality is. And then minus 0.001 times GDP per capita. So that's the slope. Okay, and then we have a regression line for the college enrollment rate also. And here, when we are using the college enrollment rate, if that's 0, I've got a higher estimate to begin, of 47.7 or 47.8 deaths per 1,000. That's going to be my guess or my estimate if there's zero college enrollment rate. And then for every increase in the college enrollment rate, I'm going to decrease my infant mortality by 0.65 about babies. And for the GDP, this is for every dollar of GDP per capita, I'm going to decrease my infant mortality by 0.001. Okay, so those are the numbers independently. Now I can run a regression where I include both GDP per capita and college enrollment, and look what happens. This estimate, the slope on the GDP per capita, that gets smaller. I go from 0.0010 to 0.005, and the college enrollment effect also gets smaller. So I go from a minus 0.6481 to a minus 0.5091. What's going on? Well, what's going on is that some of the income effect was actually capturing education. And when I control for education, when I control for college enrollment, the effect of the income, I can see it more clearly. It's half. It's half the size. Some of it is income, but some of it is also education. And then when I look at college enrollment, some of this is picking up the effect of income, because in places that have more income, there tends to be more college enrollment, but not exactly, right? And so when I separate them out, I'm able to get how they affect what's really going on with both of them being controlled. And so this one doesn't go down as much, but still it's a smaller estimate. These estimates are better because they're giving me the effect of income when I'm controlling for college. I'm controlling for education. Okay, so we're going to go over this in class. This is a really good concept to understand, and we'll go over that again to make sure everyone is clear on that. Okay, and again, you've seen this before. This is from, I think I pulled this off of a practice exam number 2. Consider the following model that shows the relationship between crime rates, age, police rate, and the average temperature. And so this is a regression that's come out. So this is the intercept. Here's the betas for the different predictors or the different explanatory variables. And Christina asked you, what's the change in crime for a 1 unit change in age, and the answer was 0.03. And she asked you what's the change in crime for a 1 unit change in, it looks like the police rate squared, but anyway, it's the beta there. So you've seen this before. Okay, next up, generating and interpreting regression estimates.